All right, so picking up where we left off last time, uh, we were talking about how covalent bonds form, and we left off with that the bonding capacity is called the atom's valence. Okay, so this might be easier with an example. So carbon, which can bond with four different things because it has four electrons that it can share, has a valence of 4. Hydrogen, which only has one electron and only needs one electron, has a valence of 1. Okay, so this is pretty simple here. It's just a way of referring to how things can be put together, and how many different things can come together in one spot. All right, now atoms in a molecule attract those electrons to varying degrees. Okay, this introduces this concept of electronegativity. So an atom's which is defined as the atom's attraction for the electrons in a covalent bond. The more electronegative an atom is, the more strongly it pulls those shared atoms towards itself. And this has ramifications. Okay? Now, electronegativity can be represented on the periodic table through color coding, and you can see this upper right-hand corner has the most electronegative element, which is fluorine. Next to that is oxygen. And coming in at a third is nitrogen and chloride. Okay. Now, if you recall, both nitrogen and oxygen are one of the 4 major contenders in organic matter or in organisms. Remember this. Hydrogen, carbon, nitrogen, and oxygen make up 96% of all the elements in living matter. Okay? Now, why this is the case is the fact that this side of the table has the most protons for the size of its shell. Okay, so here we have a lot of protons, and it's only in the second shell. So consequently, those positive and negative charges are very close together, and there are a lot of them. So consequently, this atom is smaller in diameter than some of these others. Okay, and this makes it more electronegative. Don't worry too much about that. Let's more be interested in what the outcome of this electronegativity is. And that is, you can have those electrons being shared pulled off kilter by something that is very electronegative. Okay, so here in water, we have something, oxygen, that is very electronegative. Okay, it's hoarding the electrons. So consequently, those electrons that are shared in the space between the hydrogen and oxygen tend to be pulled more towards the oxygen. This creates a scenario where the hydrogen is more or less a proton sticking out of the side of the oxygen. Okay? That gives this region of this molecule a slight positive charge, or a partial positive charge. The same is true over here. Consequently, since the electrons are gathered around this center, this portion of the molecule becomes partially negatively charged. Okay? These covalent bonds, which are unbalanced, are called polar covalent bonds, and it produces these partial charge characteristics. And interesting things can happen because of that, which we'll go into in a few minutes. Okay? Now, when this doesn't happen, when those electrons are shared more or less equally, we refer to that as a nonpolar covalent bond. So when you have carbon and hydrogen bonded together, those electrons are equally around the hydrogen as they are around the carbon. And there is no partial charge associated with it. This nonpolar versus polar covalent bond dichotomy is actually what produces the effect of having fats separate from water. So if you mix oil and water, they in fact don't mix. All of the water stays together, all of the oil clumps together. This is actually why, and we will explain this further in other chapters. All right, so that is covalent bonds. So let's move on now to the second, which is ionic bonds. And this is a scenario where instead of sharing the electrons, one atom can strip the electrons off of the other atom. So one atom gains an electron, one atom loses an electron. Perfect example of this is from sodium to chloride, which produces salt. Again, sodium no longer blows up in water, chlorine is no longer toxic, and as a result of this, both of these atoms have a charge. And this isn't a partial charge like we were talking about with polar covalent bonds. This is a full charge. Okay? These charged atoms, or sometimes you can have charged molecules. We'll touch on that another time. These charged atoms are called ions. So you end up with not equal amount of protons versus electrons. So consequently, there is a charge to those atoms. Okay. So a good way to show this graphically is here we have a sodium atom. If it could just lose this one electron, it would have a full outer shell in the next shell down. Chloride just needs to gain one. Perfect partnership. This electron leaves the sodium and goes to the chloride atom. Okay, it loses it, the sodium loses it altogether. The chloride takes it and keeps it. Okay. This has several effects. So number one, sodium is now going to be positively charged because it has 10 10 electrons, but it has 11 protons. Okay, chloride is the opposite. It now has one extra electron, so it is negatively charged. Another side effect of this is the occupancy in the outer shells is what makes an atom bigger or smaller. So you can see that both chloride and sodium have similar sizes here. After the effect, sodium is now much, much smaller. Okay, and it is physically, in reality, smaller. Okay. Now, once this happens, you have a positive charge sitting next to a negative charge. They are going to be attracted towards each other. Okay, because remember, opposites attract. Now, we have names for these charged ions. So when we have a positively charged ion, we call it a cation. Okay? When we have a negatively charged ion, it's called an anion. So here we have the anion, and here we have a cation. Something that may be useful to you is people seem to love pictures of cats, so cat is a positive thing. I don't know. That's the best I've got. All right. When you have this attraction between cations and anions, this is referred to as an ionic bond, and it tends to hold things together. Okay. Now, compounds that are formed by ionic bonds are called ionic compounds. Another name for this is salts. Okay. As you know, or as you may know, table salt isn't the only kind of salt. We have a plethora of different salts, okay? And this is all from these ionic compounds. The salts, table salt included in this, are oftentimes found in a structure known as a crystal. Okay, so I'm going to give you an image of a crystal, and crystals have repeating patterns in them. And this is very easy to understand with sodium and chloride, because here we have chloride in green, which is negatively charged, and we have sodium in yellow, which is positively charged. We can just simply alternate, and the next level down, we alternate with one shifted over. So now we have a sodium atom completely surrounded by chloride atoms. Okay, this tends to stick together and form this crystalline structure. Now, this isn't as strong as covalent bonds. There are things that can come in here and interfere with this. Essentially, any other ion that comes into the picture can disrupt this crystalline structure. Okay. Water can come in, and since water has a partial charge, it can interrupt this, which is why salt dissolves in water. Now, in addition to these strong chemical bonds, covalent and ionic, we also have weak chemical bonds. Okay, and I'm going to start to dive into weak chemical bonds, but we will be coming back to the idea of weak chemical bonds again and again. Okay, the reason why we'll be coming back to it over and over again is while the strongest bonds in an organism are covalent, weak chemical bonds are indispensable. So many of the large biological molecules, which by definition are held together by covalent bonds, are held in their functional form by weak bonds. Okay, so an example of this would be a protein which has a long linear structure, and it folds up into a three-dimensional shape that has a job. Okay, that three-dimensional shape is all about weak bonds. Holding the string together is these covalent bonds. Okay, another thing about weak chemical bonds is they can be reversed, which allow things to adhere and then come apart, and it allows us to use this for signaling, for all kinds of different purposes. Okay, and we'll delve into that much deeper. So let me give you an example of a couple of weak bonds. One is hydrogen bonds. So hydrogen bond is when we have a hydrogen atom covalently bonded to something electronegative. Okay, this means that there's going to be a partial positive and a partial negative charge, and this is going to have consequences. So example here is both oxygen and nitrogen are electronegative in character. So here we have water. Hydrogen has a partial positive charge. Ammonia, which is nitrogen and hydrogens, the nitrogen has a partial negative charge. These are going to be attracted to each other. And in fact, water is attracted to itself, which has huge consequences. Okay? This formation where we have this hydrogen attracted towards the electron cloud over here is actually very strong and stable. Okay? It's much weaker than covalent or ionic bonds, but when you link a bunch of these together, it can have a Velcro effect. Okay? Another time that this can happen is with van der Waals interactions. This can happen when we have actually, I'm going to have to pick this up on part 3.